Hi, guys. We'll give it another minute or so, and then we'll we'll start. How you guys doing?
Good morning.
Good morning.
How are you?
Morning.
I'm good. I'm doing good. I can't believe we're coming up on the end of the semester.
You know, right? You said this is the last one, right?
Well, so today,
Last lecture. I mean,
last
sorry.
lecture of new material. Yeah. So effectively, you're right. What we can expect, right? So today we're going to wrap up chapter 3.3. I'm going to roll through a bunch of examples. I'm going to do some classwork for 3.3, and then on Monday, I think we won't have class on Monday because I'll make the 2 quizzes available starting in our class period. Okay, so you'll have a half hour for each quiz plus 15 minutes for each quiz, to 15 minutes to take a picture and upload it to our Canvas page. So the quizzes are on Monday, and then I think our homeworks are due on Monday, and then our problem set's due on Wednesday, right? And then our project is due on Wednesday. And I think what I'd like to do on Wednesday, and I'll put up an announcement today, what I'd like to do on Wednesday is have you guys present your projects to class. And it's really informal, right? And what I'll do is I'll share the screen with you so that you can discuss your work and talk about it, 5 minutes, maybe 10 minutes tops, really informal. You won't be graded on the presentation, you'll be graded on the project report and the math work that you did. But the presentation is just so that we can all hear and share like what everybody else has been working on. Because I think that can be fun to see what other people have been working on. Plus, it will give you a chance to practice presenting in an environment where, people are not hostile, right? This is not a hostile audience. And so it gives you a chance to practice things. So you can expect that next Wednesday. So today is the last day of actually, class material. And really what I'm doing is I'm working through examples today so that you guys can see, how things work and what we're going to do. So it's all pretty wild. But why don't I go ahead and get started on some of that stuff so we can wrap that up. So I'm looking at our lecture examples. This is example 4. We're going to use Euler's method to solve the balloon equation. And I'm going to do a quick review of what do I mean by the balloon equation. This was from a previous chapter. It was about like related rates, right? Where we have a spherical balloon. We usually model things like you can imagine, I know balloons in real life aren't spherical unless you buy like that special kind, but I've got this, here's a radius, and then we always measure the radius right at the equator, the largest part of our sphere. So we've got this balloon. We always, in a lot of these simulations, we model it using some kind of a geometric shape. Like a sphere is really easy because it has very specific geometries to it, so we don't have to like try to do other kinds of calculus designs to figure out what's the volume of that balloon shape. But spherical balloon. So we have, this says the problem was that we have a volume is increasing, right? So the person's blowing up the balloon. So the volume's increasing at a rate of 8 cubic feet per minute, right? And then, so that's our given, this is actually our dV dt, right? So our change in volume over change in time, right? And then the question is, how does the radius increase, right? At a constant rate or not, constant rate or not, we're not sure. So this is part of what we're going to try to figure out. Okay, so let's write down, so our volume, this is from a sphere. So volume of a sphere is 4/3 pi r cubed. Okay, this just comes from geometry. And so now if I go to take the derivative, because derivative tells us the change in something over something else, change in volume over time. So it's a rate of things, a rate of change, right? So if I say I'm going to go dv dt equals 4/3 pi, those are just like constant terms, coefficients, right? So, and then I'm going to take, I have to go d dt of r cubed, right? So when I go this d dt of r cubed, I can say, okay, this is 4/3, whoops, that's a 3 pi, taking the derivative of this is like dr dt. I'm taking the derivative of the radius with respect to time. That's going to be equal to 3 times r squared. So that's my power rule for derivatives. Now I have to do the chain rule dr dt. And that's actually what I'm going to be solving for. Right, so let's put a little red bracket around the dr dt. That's what we want. Change in radius over time, because how does the radius increase? This is what we're looking for, dr dt. Okay, so I was given, actually, we're going to plug in what we know. I was given some things. So were we given a radius? Oh, we weren't. Okay, so let's plug in what we know. So our volume is changing at 8 cubic feet per, this comes from dv dt. I'm plugging in what I was given. So I'm going to plug in 8 equals 4/3 pi times 3r squared times dr dt. Okay, so what's going to happen, right? This cancels with that. And then I'm going to divide. I want to solve for dr dt. So dr dt. So I have to divide this thing by, divide both sides by 4 pi r squared. Okay, because the 3's cancel, so I'm dividing it by that. So now my dr dt, so 8 divided by 4, that's equal to 2, and then pi r squared in the denominator. So this is my, in our Euler's equations, we call this r prime of t. Okay, this is the change in rate of the radius over time. And what we can conclude is because of the r squared in the denominator, right? What happens is that that means it's not constant. Right? A constant would be like I would just have a number, right? I would like, this is a constant volume change. So my radius change is an equation. It's based on what's our current radius, right? And it also means because this is in the denominator, as the radius gets bigger and bigger and bigger, the radius change gets smaller and smaller, right? And that kind of makes sense, right? When I first get a balloon, it's flat, right? So the radius is, we'll call it close, almost 0, right? So I blow up the balloon. Think about what happens when you first blow up the balloon. It goes from flat to big, and then I keep blowing on it, goes, and then as it gets bigger, it goes, you don't notice it, right? So it gets really big really quickly at the beginning, and then it's still getting bigger, but it's getting bigger much more slowly. So we have multiple pieces of information, right? My radius is changing, but it changes very quickly at the beginning, but then it slows down. It's still changing, but it's slowing down in its change. Okay, so let's see, we'll write this down. That means that the balloon increases its radius faster when the radius is smaller, right? When I divide by a small number, I get a big number. But when I divide by a big number, 2 over 10 million, that's a really small number, right? So this is how you want to think about it. So it's not constant, and that's also what's happening. Okay, so that's our balloon equation. So just to remind us, like, what it is we're trying to do, where does that come from? So this is what we're going to be using, right, as our r prime when we calculate out our Euler's equation. So that's going to lead us to use Euler's method to solve the balloon equation for t less than 0.5, delta t is 0.1. So let's write down what we have, what we're going to begin with. So let's say I'm going to go r prime of t equals dr dt, which is 2 all over pi r squared. And then it looks like I forgot to give you an initial value. So at time 0, our radius is equal to 0.5. So that's also another reason why we think we can't make our radius, right, equal to 0 right at the beginning. And it's true, when you pull the balloon out of the package, it's kind of like floppy, but there's still some kind of radius there. So at time 0, our radius is equal to 0.5. So that gives us our initial condition. And now let's write down what our Euler's equation is. So I'll write it down in terms of r. So r of t, oops, sorry, I misspelled that. Should be, this is our next, but our Euler's equation always helps us to predict what's our next step up. So r of t plus delta t equals r of t plus r prime of t times delta t. Okay, so this is Euler. We've been thinking about it in terms of x of t or y of t, but r of t is, our radius function. Okay, so we're going to start at t equals 0, 0.1, 0.2, 0.3, 0.4, 0.5. Then we're going to plug it in. So at 0, we're at 0.5. Okay, I forgot to give you the initial condition. All right, so let's go ahead and start calculating our different pieces. So I need to calculate first my derivative at time 0, right? So I'm going to plug that into here. So I'm going to get 2 all over pi times 0.5 squared. So I'm going to use my pi button, right, to help me figure out what that is. So this I got was equal to 2.546. Okay, so that's my rate of change. So it's a pretty, good sized number. Our rate is high at the beginning. All right, now we're going to calculate up our next 0.1. So this is 0 plus delta t is 0.1. Okay, so now I'm going to go r of t, r of 0 plus r prime of 0 times delta t. So r of 0 was 0.5 plus r prime of 0, 2.546 times our delta t, 0.1. So this is going to give me 0.546, 0.75446, which makes sense. Our radius is increasing, right? Which is what we would expect. So let's go ahead and calculate our derivative for this time. So I'm going to plug it into here. So it's going to be 2 over pi times my radius now, right? So when I calculate that out, that's going to be r 0.7546. My radius is increased, right? So that's what I'm putting into my derivative. So my derivative is going to change values. So this is going to be 1.118. Okay, 1.118, which you can see, look, right? This is what we said, that our derivative is decreasing. Our radius is increasing, but the rate at which it's increasing is getting slower. All right, so now let's plug it in and figure out what our r is. So our next time, r of 0.2 equals r of 0.1 plus r prime of 0.1 times delta t. R of 0.1, 0.7546 plus 1.118 times 0.1. R of 0.2 gives me 0.8664. I'm going to put that in here, 0.8664. Okay. And now I get to calculate out my derivative. You guys can be doing this too at the same time on your page, and you can check your answers with mine. I like to draw lines to keep it. There's so many numbers that float around, I get lost. Sorry, that's a 9. Three. They didn't tell us if we needed to calculate the derivative, so I just will fill out the table. Great. So what we would plot on a graph is the change in radius right here. So I would do time on the x-axis, radius on the y, and we'd see that it's increasing very quickly, but then it starts to slow down. It's we're kind of reaching that spot where it's starting to slow down. It'll keep increasing, assuming it doesn't pop. It'll keep increasing, but it'll just basically taper off right at this point here. I mean it's gonna keep increasing, but the changes are gonna be so minuscule that we won't see it as we go along. So there's our table and there's our work. Okay, for our balloon problem. Okay. Well, you guys finish writing that, and then we'll talk about having two variables, x and y, where they're both dependent on each other. Okay, so that's example 4. We're going to talk about example 5. So example 5 says we're going to use it to find x of 1.2, y of 1.2. So I've got two variables. I've got initial conditions for both. My derivative of my x, watch, it's got both x and y in it. And my derivative of y has x. So there's an interdependence between the x and the y variables. Okay, so we need to take that into account when we're working on this stuff. So we're going to start off at time 1.0, our delta 1.1, 1.2. So we're only going to do a couple time points on here because we got a lot of calculations to cover. So our initial time, x of 1 is 1, y of 1 is 2. So we're going to use that to calculate our derivatives. Okay, so our first bit, let's go ahead and start that out. I'll do that down here. So I'm going to say x prime of 1, 1.0 is equal to, my derivative for x prime is 2 times x of 1.0 minus x of 1.0 times y of 1.0. Right? These are function values that I'm going to plug in. So 2 times x of 1.0 is 1 minus 1 times 2. Okay, so 2 minus 2 is equal to 0. So put a 0 there. I'm going to do my y prime of 1.0 is equal to minus t times x. So minus t times x of 1.0, which is equal to the time period that we're at is minus 1.0 times x of 1.0 is 1. So this is equal to minus 1. So minus 1 goes there. Next time up, we're going to use Euler's equation. So let's remember, we have to calculate Euler's equations for both x and y. So let's remind ourselves. So x of t plus delta t equals x of t plus x prime of t times delta t. Y of t plus delta t equals y of t plus y prime of t times delta t. These are Euler's equations. To come up with values for x and y. Okay, so let's do it. So x of 1.1 is going to equal to x of 1.0 plus x prime of 1.0 times delta t. So let's plug in those values. So x of 1 is equal to 1 plus x prime 0 times 0.1. So that's just going to equal to 1. Y, put 1 right there. Y of 1.1 equals y of 1.0 plus y prime of 1.0 times delta t, which is equal to y of 1.1 is 2 plus y prime minus 1 times 0.1. And that was equal to 1.9. Okay. Now I have to calculate my derivatives. I'm going to use my x prime of 1.1 using my derivative equations, right, from here and here. So x prime of 1.1 is going to equal to 2 times x of 1.1 minus x of 1.1 times y of 1.1. So this is 2. X of 1.1 is 1 minus 1 times 1.9, which is equal to 0.1. Okay, I'll do my y. Derivative 1.1 is equal to following it. So it's minus t times x of 1.1, which is equal to minus, I'm at time 1.1, times x of 1.1 is equal to 1. So that's equal to minus 1.1. I'll plug that in here. Now our next time frame, see how we've got like multiple things that are happening, but the x and the y's are dependent on each other. Okay, so let's do this. I need to calculate x of 1.2 equals x of 1.1 plus x prime of 1.1 times delta t. So x of 1.1, I'm going to go back to my table. X of 1.1 is 1. 1 plus x prime of 1.1 is 0.1 times 0.1. So x of 1.2 gives me 1.01. Sorry, 1.01. And now I have to calculate y of 1.2. So I'm going to go y of 1.1, y prime 1.1 times delta t. So y of 1.1, 1.9, plus y prime of 1.1 minus 1.1 times delta t. And that's going to give me 1.79. All right, so the question said use Euler's method to find x of 1.2 and y of 1.2. So that's right here. I don't have to calculate the rest of the derivatives because they told me just to stop right there. Okay, our x and y's were dependent on each other, right? So when I calculated my derivatives, I needed my x and my y's. It's kind of neat. Okay. What do you guys think? Not so bad? Okay, so what I'd like to do now, I'll scan these in and put them up on our class page later. I'd like to actually go through and do some of the classwork problems. Okay, for classwork for 3.3. And I'll do it now just so you guys can have it in a video in case you want to reference it later. This is the basis for your quiz on Monday, 3.3, and then also don't forget 3.2, which is all about integration stuff. Okay, so you've got 2 different quizzes because they're 2 different topics. All right, so I'm just going to work through. I probably won't talk as I'm working through. I'll just start working through, and then I'll do my work maybe on the side. Okay, so you guys can see that. And then I'm done. Okay, I'm going to go into the next one. Learning calc is a no-no. It's kind of tedious. Yeah. It's an exponential function. The derivative is 3 times the function. So this thing's going to grow pretty quickly. I'm gonna just move down this way here and work through problems. Oops, I think I missed a step. 2, I have 2 point. This should be, sorry, this is wrong. My bad. Yeah. There. And And then we're done for that one. Whew, that'll work. There's our table. Sure. This is a logistic. You can tell it's logistic based on its derivative form. I'm sorry, I messed up. You got space. And then we're done for that one. We'll do the next page. All right, so we have x and y. So let's write out what our Euler's equations are. Okay. Starting off at 0. Okay, so y of 0 is 0 0.5, x of 0 is minus 0 0.5. And then we're given derivatives here and here. I'm sorry. It's 0.824. But it's kind of big. Okay. All right, next one up. Oops. I did. I keep putting the decimal in the wrong spot. This is a positive 0.5. Oops, that's a 2. 2. I'm going to steal some space here. To do my last bit. Okay, we can stop here. Those are the answers that we were looking for. So there's our final table. Phew, a lot of work. All right, that's chapter 3.3, guys. Basically all set with chapter 3.3. And this is the kind of thing you'd see on a quiz. Probably, maybe not something like this. This would take you forever. But you know, the general idea. Okay. So I can let you guys go early. And then I have office hours today. If you guys want to stop by and ask me any questions, I'll be around from 1 o'clock to 2 o'clock. Okay, guys, have a great day and have a great weekend. Don't forget, no class on Monday, but there's a quiz.
All right, bye.
Bye, guys. Take care.